floor is yours.
Okay, thank you. Let me share the screen. So I would like to thank the organizers for the invitation to speak here. Some comments before I start the talk. Okay, I'm going to talk about collaboration with many people, which I'm putting here. I'm going to talk about vortices on the sphere. So I want you to share some pictures of Saturn. And this is Jupiter. These are NASA pictures. And you can see here like a vortex at the center and then an hexagon of vortices. And here you have one vortex at the center and then 8 in a polygon. And then you can, maybe you can see here 1 and then there are 5. It's a pentagon. So I'm going to talk about more complex structures than more complex solutions that I'm showing here. Some of them are really periodic solutions. Okay, so I'm going to start with equations. I'm just going to describe vortices by functions in the unitary sphere, n functions from J1 to n. The system of equations is a Hamiltonian system, so the configuration space is a manifold M, which is n copies of spheres, each copy for each vortex. So the Hamiltonian in that manifold is just h of v is just the sum of logarithm interactions of the distance between Bj and Bi. And the symplectic form in the manifold is just a symplectic form made of the sum of the symplectic forms of it's just the area form for each sphere. Okay. So this is a Hamiltonian system on a manifold. So my first step is going to look at it as if it were just a manifold in plane. So for that, I'm going to use a symplectic projection or symplectic coordinates for the sphere. So I'm going to project the sphere, so the sphere of radius 1 into the complex plane. So the simple projections, the simple projection is if you take x, y, z in the unitary sphere, then you send that map just taking x plus I, y minus over 1 over c, and that falls in the complex plane, and that's just a classical stereographic projection. So now my coordinates are going to be complex coordinates for the spheres, right? So the first thing I'm going to do before doing anything else, I'm going to do both at the same step. I'm going to change to rotating coordinates. Why? Because I want to look at the relative periodic solutions arising from relative equilibria. So relative equilibria in the correct rotating frame is going to be just an equilibrium. So I'm going to go from the stereographic projection coordinates for the sphere to a rotating frame, which is made in terms of u of j. So basically, if I put this Hamiltonian with this symplectic form, and then I write the Hamiltonian in the stereographic projection with the rotating frame, then I obtain this. Oh, there is a mistake here. This should be u. Sorry. So h of omega of u is equal to omega 5t of u plus this, everything depending on u. So this is the Hamiltonian in the rotating frame, seen from the chart of the stereographic projection, where 5 of 3 is just the third component of the momentum map, which is given here. Okay, and the symplectic form on the sphere, given with this, is just the symplectic form, which is the sum of the area forms, right? Given on each one of the spheres. So this is my Hamiltonian. The mistake is just replacing in all this part q by u. and here also Q by U. Okay. So now this is correct. Okay. Now this is my Hamiltonian. This is my symplectic form in rotating frame. So if I write explicitly the equations are going to be just this term, which appears just from the area of the sphere seen in the stereographic projection. Is very classical. I, uj, I is giving the symplectic structure in complex coordinates, and then the gradient of h of omega of u, where the gradient of h of omega is just given explicitly here. Okay. Now, this is where things start to get nice. So this system represents the system for n vortices on the sphere seen from the stereographic projection chart and in a rotating frame with frequency omega. Okay, so for that Hamiltonian system, I have an equilibrium, which is really a relative equilibrium, which is a polygonal relative equilibrium, right? Why the polygonal relative equilibrium? Well, just because these structures really appear in nature. So that's going to be my starting point. So it's very easy to see that if you take the positions of the vortices in the components A1 to AN, right, where AJ is equal to a radius e to the ij zeta. Zeta is going to be the angle 2 pi over n. So basically, this is going to be just a polygon with the radius r. Okay, so if you put that positions in the stereographic projections of the polygon on the plane, then this is going to be a critical point or an equilibrium when you put the frequency omega equal to 1 minus n minus 1 multiplying 1 minus r to the 4 over 8 r squared. So basically, this is a polygonal relative equilibrium, right? Regular n polygonal relative equilibrium of radius r. And this is going to be precisely an equilibrium when the frequency is equal to this number. Okay? And this is my starting point. So before explaining the main theorem, I would just like to explain a little bit about physics, right? So I can write this explicit Hamiltonian system in vectorial form. So for that, I'm going to define the matrix J of U. So J of U is just a direct sum, or in the diagonals, having these numbers, which is 4i over this number with un, and then going to u1, going to un, right? And if I define that matrix like that, then this system is just Ju applying to u dot equal to the gradient of h of omega. And then once I have this system, right, I know that the polygonal relative equilibrium for this frequency with this radius is a critical point of h of omega. So that means it's an equilibrium. So I can linearize this system at the polygon, right? And the linearization of this system at the polygon is very simple. It's just u dot equal to j a minus 1. A is the polygon. The Hessian of h of omega taken at a, and then this matrix applied to u. So this is what people call physicists call normal frequencies and normal modes of oscillations. So that's just a name for basically the normal modes are the periodic oscillations of this linearized system around the equilibrium, and the frequencies are just the frequencies of those normal oscillations. So basically, what I mean by a frequency of the normal oscillation is the value nu k, right? Such that I nu k is an eigenvalue of this matrix, Why? Because if this is an eigenvalue of this matrix, then that means that this linearized system has periodic solutions with frequency nu k, and it has at least one two-dimensional invariant subspace where all the solutions are periodic with that frequency nu k. Okay, so if one take this equilibrium and one linearize this system and one obtain these matrices, so it's not too difficult to compute using the fact that one has a lot of symmetries for the polygon. It's not difficult to compute that the frequencies of the normal modes of oscillations are these values. So here I have in terms of the radius of the polygon, and then some numbers. Here I have in terms of the radius as well. And then there are some numbers that appear, which is sk, s1 minus sk, 2s1 minus sk minus 4s1, multiplying to this function of the radius. So what are the numbers sk? The numbers sk are just very simple. It's just k multiplying to n minus k over 2. And this is for k from 1 to n. So these are the normal frequencies, which is the eigenvalues of this matrix are I nu k for k going from 1 to n. Okay. So these are my normal frequencies, the frequencies of the normal modes of oscillations for k going from 1 to n. So why people study this? Well, because the linearized system is the best approximation that one can have at the equilibrium for the nonlinear system. And the first thing that one can ask is if is there any of those periodic solutions for the linear system that can persist for the nonlinear system. And this is the content of the Lyapunov-Center theorem, the Weinstein-Moser theorem, and many other theorems. Okay, so in order to apply those theorems, one needs to satisfy some conditions. So something that I want to say is that you can see that nu of n is equal to 0. Why? Because when k is equal to n, this is 0. So this is 0. Everything is 0. Okay. So that frequency actually exists due to the invariance of the problem on the SO2 rotations. So if one can, if you want to prove the existence of periodic solutions, relative periodic solutions close to the polygonal relative equilibrium, you need to first consider or to take in consideration the symmetry of SO2. Moreover, actually, there is a resonance. What is a resonance? Well, there is a one-to-one resonance. What does it mean? It means that nu of k is equal to nu of n minus k. Why? Just because sk is symmetric. If I replace k by n minus k, this is going to be equal to sk. So this only depends on sk, and for that reason, nu of k is equal to nu of n minus k. That means that if I choose a frequency nu of k, the dimension of the invariant manifold invariant subspace foliated with periodic solutions of frequency nu of k is going to be 4-dimensional, right? And that's a problem. That's a problem. These two things are a problem. Having a frequency 0 is bad for the Lyapunov-Center theorem, and having a one-to-one resonance is bad for applying the Lyapunov-Center theorem. The Lyapunov-Center theorem requires not having resonances, not having these 0 eigenvalues. Okay, so the classical Lyapunov-Center theorem cannot be applied. For what? The Lyapunov-Center theorem cannot be applied in order to show that the periodic solutions of the linear system persist in the nonlinear system. And those periodic solutions are going to be relative periodic solutions close to the relative polygon. Okay. Okay, so I'm gonna apply this Lyapunov-Center theorem. What else can one do? Well, instead, it would be possible to apply the Weinstein-Moser theorem but just after a reduction by the group of the action of the group S of 2. So what would be the procedure in order to prove the existence of those periodic solutions? Well, you just reduce by the action of the group of the rotation SO2 for this Hamiltonian system. That's not too difficult because it can be writing like instead of having complex components U, you can write them in terms of radius and angle. And then in that case, you can reduce it just by eliminating one angle. And for that reduced system, then you can apply the Weinstein-Moser theorem in order to be able to prove the existence of solutions when you have this double eigenvalue. Okay, that would be one procedure. What's the problem with the Weinstein-Moser theorem? The problem with the Weinstein-Moser theorem is that it's just a local result, and also most of the time it does not imply the existence of continuous families of periodic solutions. So instead of that, I'm going to show now my main theorem. So my main theorem is it does a little bit more. So in order to explain what is the main theorem is, okay, I want to find periodic solutions close to the polygon with the starting frequencies, these starting frequencies, okay? So, but those periodic solutions, like for the nonlinear system, really depends on the frequency. Most of the time. So in order to catch that dependence on the frequency, I'm going to suppose that I'm going to target a periodic solution which has a period 2 pi over nu, right? So I can renormalize that periodic solution with this transformation such that x of j is 2 pi periodic. This is just a rescaling in time, such that I will obtain the frequency in the differential equation as a parameter, right? So now this is a theorem that it was proven in 2019. It was using a equivariant degree by Jorge Isen. I will go a little bit on the main ideas later. So what is the main theorem? For each positive frequency nu of k, why positive frequency nu of k? Because, well, this needs to be real, okay? So because if this is imaginary, then this is complex. So for each one of those real frequencies, the polygonal relative equilibrium has one global family of periodic solutions, right? The global family is being represented in the normalized functions with period 2 pi, so that's x. X is the functions with normalized period 2 pi, and nu is going to be the frequency. The frequency is now an explicit parameter of my equation. So this is my family, and that family is arising in this space. This is going to be the Sobolev space of 2 pi periodic functions with one Sobolev derivative in the product of the planes for the vortices, right? And the frequency is going just to be a real. And the symmetries of that family of periodic solutions is going to be this symmetry. This symmetry implies that the positions of the n vortices in the periodic family which arise from the polygonal relative equilibrium is determined only by the position of one of the vortices, right? But up to a phase and up to a rotation, right? So, okay. And well, later when one does the analysis when these frequencies are real, well, that appears only for the cases k from 1 to n-1 if n is less or equal than 7, and k from n, k equal to 1, 2, n minus 2, and n minus 1 if n is bigger than 8. This is related with the fact that, of course, the linear stability of the polygon A, right, the polygon A is not going to be linearly stable unless non-linear stable, unless all the frequencies are real. And it's known that the polygon is stable only for n less or equal than 7. And for n bigger than 8, bigger or equal than 8, it's unstable. So for that reason, I will have only less periodic solutions for those cases. So now here I say there is one global family. So what is global family? Global family, it's a little bit different than one obtaining in Lyapunov-Center theorem and Weisstein-Moser theorem, because these are local theorems. I mean, the proof of existence of the periodic solutions in those two theorems is by the implicit function theorem, basically. While in this theorem, it's really, the proof is with equivariant degree. So global is something that started in bifurcation theory with a result of Rabinowitz, which improved a result of Krasnostersky, which was using just Leray-Schauder degree or Brouwer degree in order to prove the global existence of solutions in elliptic equations. So now in periodic solution, the global property means really it's really an alternative. So what is the alternative? So I have a family, which is the family of periodic solutions with normalized period to 2 pi and the frequency in this space. And this is arising from this point. What is the point? The polygon, and the frequency is the normal frequency. And now I can see that family. And that family has to satisfy in this space one of the following alternatives. The family needs to return to another equilibrium, or the family ends at an orbit with collision, or the period goes to infinite, or the Sobolev norms goes to infinite. So before giving an idea of this theorem, I want to show you some numerics, which I did in another work. This is joint work with Renato Calleja and Eusebio Zedel. It was done in a program which was developed by Duedel, which is called Auto. It's kind of standard in order for computing numerical solutions. And so what you can see in the left, right? Originally, you have your bodies in a pentagon, right? The pentagon is a relative equilibrium. Just, I am seeing these things in rotating frame. So in rotating frame, the polygon is just an equilibrium. So now there are these normal modes of oscillation. Normal modes of oscillations are just like circles going around here, right? But instead of doing just normal modes, what I am showing here is just really then what people call nonlinear modes of oscillations, or the periodic solutions I'm talking about. So what is it? You have a family of nonlinear modes, right? And then these families start to become, the nonlinear terms start to interact. So you can see here how in this periodic orbit now it's very far from being just a circle, which is a solution of the linear system, right? So this is really numerics made for 5 vortices, and we have a computation really of the family. So what is the alternative? The alternative is that this family that you can imagine here, right, is really at some point going to have a collision, or it's really going to come back to another equilibrium, or it can go like, for example, to a homoclinic, like in an homoclinic, the Sobolev norm explodes, or also the period goes to infinite. Okay, so that's like the content of the global bifurcation, which really requires a topological argument. The topological argument is given by the degree theory. So in this left picture, what I'm doing is the graph of the vortices of the periodic solutions in the rotating frame in the stereographic projection, and on the right you can see the exactly same solution in the rotating frame, but on the sphere, right? And this is another solution in the same family, right? You can see how it starts to develop some more complex pictures. And then when you see this picture on the sphere, it's just a picture on the right. Okay, so I hope I present an idea of what is the content of the theorem. So now I'm going to dive a little bit about the ideas that are required in order to prove the existence of these families, global families of periodic solutions. Right? So I'm going to start with a variational setting for the problem of finding the periodic solutions. So a nice variational setting for finding the periodic solutions for Hamiltonian system is what people now call Rabinowitz-Floer variational setting, right? So suppose that I have a contractible periodic solution U of t of this Hamiltonian system in the manifold M omega, and here I have a problem of notation. Omega here is the symplectic form, and omega here is the frequency of rotation of the relative equilibrium. Right? So for this Hamiltonian system, right, the periodic solution, according to the Rabinowitz-Floer variational setting, is just a critical point of the following action. It's going to be the integral over the path of the Hamiltonian of U of t over time, and then it's going to be the integral of the pullback of the curve of the symplectic form. U tilde, so what is U tilde? U is a periodic path on the manifold M, right? So U tilde is going to be an extension to a disk. So U tilde is a function from a disk to the sphere, right? Which is an extension of U. So what means an extension? Well, U tilde restricted to the boundary of D is just U. So if I do a graph for the sphere, it would be like, I have the sphere, right? And then here I have a curve U, right? So U tilde is just extension to a disk. And so this is U tilde. Now, this is Rabinowitz-Floer setting. So periodic solutions which are contractible are critical points of this functional. There is a little problem, which is it might happen that the manifold M can have extensions. How to say it? Well, the problem is that for manifold M's, such that the second group of the manifold is non-trivial, right? That means manifolds which are spherical. Then in that case, I can have different extensions. For example, in the case of the sphere, I can have the extension which is a complement of that domain. And in that case, I can have different extensions, and the maps A or the functionals A can have different values depending on the different extensions. But once I choose one extension, everything works fine, okay? So in our case, the extensions are going to be given naturally because I am going to do it in the stereographic projection. So in the stereographic projection, I am always going to remove the south pole. And because I remove the south pole, the extension is only the extension that I can do in the plane. So in using the stereographic projection, this integral is just going to be, for our problem, it's just going to be the sum from j1 to n of a of u of j, where a of u of j is just the area bounded by the periodic curve on the sphere. I mean, u of j is a path in the complex plane, so I can send it to the sphere with the inverse of the stereographic projection, and then that's going to be bounded a disk, and then a of u of j is that area, right? So in this picture, if I draw here the plane, right? Let's say that red is going to be projected into something here, right? So there is only one natural extension, which is this one, because the other extension would require to pass by infinite. Okay, so and with those extensions, the action is well defined. So, so actually, I talked before about the scaling, because u of t can have different periods. So if the period of u is 2 pi over nu, as I said before, right? Because I want to target the periodic solutions arising from the equilibria, and that family that really depends on the period, and then I want to use a functional setting, a nonlinear functional setting, then I'm going to rescale the time in order to have x of t with this rescaling always being a 2 pi periodic. And the action for x of t is just going to appear here at nu, right? And that's it. So what I'm saying is that the critical points of this action, which is just minus nu of the sum of the areas bounded by the curves x, j, and then the integral of the augmented Hamiltonian, right? Those critical points are going to be the periodic solutions of this theorem. That's it. Okay? Now the question is how I'm going to be able to prove the existence of periodic solutions for that action, right? I didn't say in the theorem before what was phi. Of course, in this space, I am taking collisionless curves, and I didn't say it. So now I'm going to say it, which is I'm going to define phi as the point such that there are no collisions, and then so phi is a collision set, right? And then I'm going to define the Sobolev space of 2 pi periodic functions with one derivative, such that they don't have collisions. Okay. So now the gradient of the action A actually is an operator which is not difficult to compute. So before I define this matrix, right, J of U, so actually the gradient of the action is just nu. Maybe there is a problem with the sign. I changed sign, but okay, it is similar. So I have nu of that matrix J of x, x dot minus the gradient of h of omega. So this is kind of a simple way of writing the system. And this is just the gradient of the action. And this is well defined in this space. So this is a nonlinear map going from the Sobolev spaces of one derivative to no derivatives. So the critical points of the action A for this map, this gradient, correspond precisely to relative periodic solutions of the n-vortex problem of this form. So the solution e to the I of omega t xj nu t is going to be the solution, the relative periodic solution in the complex plane, right? When X, J are the components of X, which is a critical point of A. And then I can send that with the inverse of the stereographic projection to the sphere and see how the solution look like. So now what are some technicalities? I think I have 20 minutes. Okay. So some technicalities is, I will go very fast. So the action A is invariant. That's where things start to get interesting. The action A is invariant under the action of a group G. What is a group G? I'm going to be fast. Is a permutations of the vortices, because I am taking vortices with equal circulations, the rotations in the complex plane, and time translations. So if I take a function x in components, if I take a function x and I want to define an action of G on that x, it's just taking the components. So sigma is a permutation, theta is an angle, phi is an angle. So if I apply that element of the group to x of J, that's going to be just rotation, permutation of the vortices, and then phase shift. Okay, so what is the interesting thing? The interesting thing is because A is G invariant, then what is going to happen is when I take the Hessian of A, the Hessian is going to have a kernel at least of dimension 2, right? So the generator fields of the group G, which are A1 equal to IX and A2 equal to X dot, are going to be in the kernel of the Hessian. This is known, and that's a problem for proving the existence of periodic solutions, except if one do things correctly, then one can sort it out. And how is going to be sorted out for this specific problem? Well, because it's variational problem, right? Actually, there are conserved quantities generated by the action of the group G. This is by the Nether theorem. More explicitly, that is, the field gradient of A is orthogonal to the infinitesimal generators f of Aj. That means the gradient of Ax is orthogonal to Aj of X. And actually, this orthogonality is nothing else that for J equal to 1, I have a, this is shift. For J equal to 2, this orthogonal condition, right, with this generator is just, no, it's fine, sorry. For J equal to 1, this orthogonal condition, when I put here Ix, right, is just the conservation of angular momentum. And for J equal to 2, for the generator of translations in time, where I put here X dot, is just a conservation of energy. This is a product on L2. This is a product on L2. Okay, so it's a L2 product. So it's an integral. So the only thing that I want to say is that if I want to do classical bifurcation for the gradient of X, the problem is that for doing classical bifurcation for the gradient of A is not so simple. Why? Because there is a kernel of always a kernel of dimension 2. And also, but the nice thing of the gradient system is that there is also 2 conserved quantities. So the basic idea of topological degree is that it's going to do a match between the 2-dimensional kernel and the 2 conserved quantities. So now how it goes. So the gradient actually is SM cross SO2 cross S1 orthogonal in the sense of definition of orthogonal degree by Ise, right? So what I can do is that since A is an equilibrium in the rotating frame, if I obtain the linearize of the gradient, that means the Hessian of A at the equilibrium, and then I apply it to X, I can decompose that very simple in Fourier components. Why? Because this operator does not depend on time. So that's just the sum of matrices in the applied in the components of the Fourier of XL. If A is not an equilibrium and it depends on time, this is not true. And then I obtain kind of convolution, and it's very complicated, right? But because it's an equilibrium, it's autonomous, this operator, and then I obtain that. Actually, it's very easy to compute what is this matrix. This matrix is just nu I JA minus the Hessian of H of omega at A. Okay, why? Because what is the Hessian of A at the equilibrium? Well, the Hessian of A at the equilibrium is just the linearization of this at the equilibrium, and the linearization is just nu J of A derivative Hessian of H at A applied to X, right? So in order to apply the orthogonal degree developed by Jorge Ise, I need to do first a Lyapunov-Schmidt reduction to finite dimension. So I'm not going to go into details. What Lyapunov-Schmidt reduction? Well, I decompose the space of periodic solutions into two parts. A truncation for Fourier components less than P, and the complement. So the complement is going to be solved by implicit function theorem, global implicit function theorem, in terms of the components of the projected part, such that critical points of A in this big space, critical points, zeros of this map in this big space are going to be critical points of a functional infinite dimension. Finite dimension because zeta is the projection of the Fourier components, and zeta is going to be finite, right? So now the fact that the polygon is a relative equilibrium that is not degenerated is going to imply that this number sigma, which is just the determinant of the matrix M at 0, restricted to the slice, W is a slice of the SO2 orbit of A, this is different from 0. Why? Because when nu is equal to 0, this disappears, and this is just the Hessian, and that's just the definition of an equilibrium being non-degenerated, right? So now this is the theorem. Let n of nu being the Morse index of the Fourier component of the Hessian of the action at the equilibrium, right? Then I can compute the orthogonal degree of the reduced action around this point. This is like the index around the point A and nu for the gradient. And the point is that the degree, the Brouwer degree, is just a number. So what is the orthogonal degree? The orthogonal degree is just like a number for each isotropy group, right? So the orthogonal degree is going to have many numbers which are in different copies of zeta. And this number, these represent the generators of that zeta, right? And when I compute this, I'm going to obtain that this is just sigma n1 of nu for the for the trivial group, and so on for groups where I have the action of time with isotropy group C of n, right? So the properties of the degree is going to imply that if the Morse index changes at a point nu 0, then there is going to be a bifurcation arising from that nu 0 with that isotropy, right? So the main theorem follows basically from the fact that the Morse index of these matrices are given here, right, is changing precisely at the frequencies of the normal modes nu k. You can see easily that this is going to be an eigenvalue of this matrix if and only if nu of k is in the kernel of this matrix, just basically by multiplying this part to the right. Right? So that's the idea of how the theorem is proven. And then I think I have how many time do I have? I think
you have still like 2 minutes left or something.
Yeah, 2 minutes. So I would just like to mention with 2 minutes pictures. So basically, along these families of periodic solutions, what you can find is a dense set of choreographies. I'm not going to go into the details of how you can find those dense set of choreographies. But what you can see here is exactly the same periodic solutions. This one and this one are exactly these ones, except that before I have them in rotating frame. And here I have in inertial frame, I mean, not in the rotating frame. So I have dense sets of choreographies for the n-vortex problem. And so this is in projected plane, and this is in the stereographic projection. And then I will take 2 more minutes from questions. So one can ask, okay, so what else can do? So now currently I'm working with these people in order to try to prove, in order to prove the existence of periodic solutions as in the previous theorem from the polygon, but for more complex relative equilibria. So these are examples of relative equilibria for 12 vortices, right? How they are going to look, instead of having a polygon in the complex projected plane, I'm going to have like nested polygons in the complex projected plane. But the same theorem can be applied. And then something that I wanted to say is, okay, so what else can be proven? Is it possible to prove the existence of periodic solutions arising from other equilibria, not relative equilibria, equilibria, like the Platonic solids? And then when I was trying to address this problem, I found the following problems. We cannot make a similar procedure because the action of SO3 in the stereographic projection is not a linear action. What I want to say is that the theorems that I showed you works for a Hamiltonian system, like in vectorial spaces with linear actions, right? And the action of SO3 is not a linear action. It's actually a subgroup of the Mobius group of transformations. So I cannot apply the same theorem. So what else I was thinking that we can do? Well, we cannot apply the equivariant Weinstein-Moser theorems, for example, made by Montaldi, because the equilibrium has an SO3 orbit. I'm not talking about relative equilibrium, I'm talking about an equilibrium. And equilibria really are in SO3 orbits. What else can I do? Well, in theory, it's possible to make a Mersenne-Weinstein SO3 reduction, but in practice, we try it, but in practice, to make those reductions and to compute the reconstructions of dynamics is not an easy task for n large. It is actually a little bit difficult for n equal to 4. So finally, what I did in a joint work with Luis Garcia Naranjo was going around it, and by looking at we construct periodic solutions by means of discrete reduction of the system to twist subgroups of the full group of symmetries of permutations and SO3 rotations. The solutions just look like this one, and then I just want to show pictures, right? So the picture is in the left. I'm going to target solutions of the n-vortex problem, which are determined only by one vortex, and then there are going to be fixed vortices on symmetric places, and then there are going to be relation between different positions of the same vortices by a group K, which can be the diedral, tetrahedral of diedral, or icosahedral. So in this case, this is for 12 vortices on the taking a tetrahedral group. So what you see here is like the reduced system for only one of the vortices. And then, for example, this point, red point, yes, this point represents the tetrahedron where you have triplet collisions at each one of the points. And then you have like this periodic orbit. This periodic orbit is going to represent 3 vortices going around each one of the points of the tetrahedron. And for example, you have green here, and then green represents just the this icosahedron. And you have periodic solutions, which are green, which are vortices going in circles around the icosahedral equilibrium. That's it. There are some references there.
Thanks for the talk. Let's thank the speaker.